Hey, hello everyone, this is Manas, your friend and tutor, and as always I'm back with another video. Well, today we're going to be talking about fixed beams, and this is probably the penultimate problem in this video series, and this is basically, well, based on a concentrated couple. As you can see, there is a couple acting at point C 4 meters away from end A. Now guys, if you have been watching my previous videos, the first case or the first example that we took was based on a point load. Second example was based on a uniformly distributed load, and this is by far one of the finest examples. Here we have a concentrated couple, and what we are supposed to find is the fixing moment at A and B as well as the reactions at A and B. And apart from that, I'll also let you know, rather I'll demonstrate how the SF, that is shear force and bending moment diagrams, can be drawn. Man, the temperature is really very high. It's almost 45 degrees maximum in Raipur today. It's really very high temperature. Oh. And basically this is my third attempt into making this video, because as soon as I start, there is a power cut. No light, no video. And so I'm praying to God, प्रार्थना करता हूँ ईश्वर से कि अब लाइट ना जाए, वीडियो बना पाऊँ. चलिए, let's start. Okay. So the first thing in any problem based on fixed beam is to take the moment at a section of the beam. So what we'll do is we'll take the section from the left hand side, okay, and in such a manner that everything will be covered up. So it's going to be something like this. Do watch. We are going to take a section over here like this. Okay, now let me make the portion of the beam towards this side, and it's something like this. Done and done. So over here, obviously we've taken the section from this left side. So at a distance of x, we have taken the section. Okay. Then if you take the section from the left, the moment at this point, this is what we call as mx. Secondly, there is a couple acting over here. Let me extend this slightly here. And this is a clockwise couple. The magnitude, well, we know that very well. 150 kNm. Apart from this, if you watch, remove this fixing support. Okay, so this can essentially be replaced with a reaction. Let's name this as RA simply, and there is going to be a hogging moment. Okay, let's say fixing moment. Let's name it by MA, and a similar fixing moment is going to act here also. Hogging nature at B, that is MB. We are going to calculate all of those things. Not to worry. Right? First step in any fixed beam problem is to take the section. And from where have we taken the sections? You have taken the section from the left hand side, from left. Okay? And when you do that, this bending moment is sort of an anti-clockwise nature. If you take the section from the right, the bending moment mx would be automatically clockwise. Not to worry. So what we'll do is we'll take the moment. We will rather take the moment about this very point, and equate it to 0. Moment. Okay, moment about which point? Moment about this point is equal to 0, and let's work it out. So anti-clockwise I always take it as positive, clockwise I always take it as negative. Remember this, starting from this mx, moment across this cross section, that is mx. It is anti-clockwise, therefore a positive sign. Let me put a positive sign, and this is going to be mx. Anything else? Well, apart from this we have RA multiplied by x. If you watch, RA clockwise, RA multiplied by x clockwise, therefore minus sign, minus RA times of x. Then we've got this bending moment, okay, or fixing moment. Anti-clockwise, that's why positive. So this is going to be plus MA. And apart from that, we've got a couple over here. This is clockwise, so obviously what you need to do is negative sign 150. But guys, there is one more thing. You can write this as 150 multiplied by 1. Okay. Let me tell you what I am essentially trying to say is this. Whenever you apply the Macaulay method, and we are actually applying the Macaulay method, you always need to specify the distance. So apart from force, you have the distance. Force multiplied by perpendicular distance, that's okay. But in case of couple or moments, you don't have anything of that sort. So what we need to do is you just provide the distance like this. This is acting how far? with respect to this point, this couple is acting at a distance of, if you watch carefully, this distance is nothing but x minus, this is how much? 4. X minus 4. Okay, so this is 1 can be replaced with, let me tell you, this is going to be x minus 4 to the power 0, and anything to the power 0 is equal to 1, and this is basically the Macaulay approach, is equal to 0. You just need to shift all of these things over to the right, and let's have the final equation. Mx is going to be equal to Ra times of x minus Ma plus 150 x minus 4, and that's it, to the power 0. And let me check whether this equation is correct or not. Where are my notes? Mx is equal to Rx minus Ma plus 150 x minus 4 whole to the power 0. Absolutely correct. बहुत गर्मी है भाई, बहुत गर्मी है. Anyway, let's proceed now. So this is Mx, and this Mx we know very well. If you apply dy ei d2y by dx square is equal to the same term, Ra dot x minus Ma plus 150 x minus 4 to the power 0. Done. Now what? You need to integrate this. You just integrate. When you do that, d2y by ds square will reduce to dy by dx. This is going to become Ra times of x will become x square by 2 minus Ma dot x, and let's say this is the first section. Okay, this is going to be accompanied with a constant of integration c1. Let me close this, plus 150 times of x minus 4 to the power 1. 0 plus 1 divided by 0 plus 1, so divided by 1. No need to write that. Now if you apply the first boundary condition, the first boundary condition says at x is equal to 0, the slope dy over dx at x is equal to 0. At this point, the slope is 0 as well as the deflection is 0, right? So this is the first boundary condition which we are going to apply. When you do that, this is 0, 0, 0, everything is 0, and when you put 0 over here, inside the bracket we have a negative term, so you have to discard this. Don't worry about this. Anyway, so we are essentially left with the value of c1 is equal to what? Is 0. So damn easy. You integrate this again. Dy by dx will reduce to simply y, and this is going to be equal to Rax cube over 6. Done. Minus Max square over 2. So c1 is 0. We know that very well. And what about c2? A new constant of integration will come into the picture. c2. Done. Plus 150 times of x minus 4. 1 plus 1, 2. Whole divided by 2. So this is our another equation. This is the deflection equation. This one is the slope equation. Anyway, when you plug in the value at x is equal to 0, now the deflection is also 0. We know that. 0, 0, 0. If you put 0 over here, inside the bracket we have a negative term. Negative term has to be discarded. Anyway, when you plug in all the values, you are going to ultimately get the value of c2 as 0. So this is essentially how you can work these things out. What we want is initially to get the value of Ra and Ma. How to proceed? There is another boundary condition that you can apply, and that is when you put the value of x is equal to 4 plus 2, because you have the slider over here. If you put x is equal to 0, we are right here. If you put x is equal to 6, we are at point P. Again there is a power cut. I need to pause. We'll be back soon. Okay, so we are back. The power is back. Let's see how long we can survive. Anyway, so what I was telling to you is that if you put the value of x is equal to 0 over here, you can put slope and deflection is equal to 0, and based on those conditions we obtain the value of c1 as well as c2. Done. Now we are going to apply the second boundary condition, which is at end point B. That is also a fixed end, and that is where the value of x, if you increase the value of x will become 4 plus 2, that is 6. So at x is equal to 6, you will have the slope is equal to 0 and you will have the deflection is equal to 0. Now first of all, what I will try to do is, let me just rewrite these equations in a better form. Let me write the slope equation and let me have the deflection equation also. Okay, so the slope equation is like this here. Let me rewrite this and then we're gonna go ahead. So it's let me write this, ei dy over dx, and this is equal to Ra dot x square by 2 minus Ma dot x. C1 is equal to 0, we know that. Okay, that's it, that's the limit, plus 150 times of x minus 4 and power 1. Okay, power nothing is by default power 1. And secondly, what I'm going to write is this deflection equation. Let me make some space because a lot of calculation needs to be done, right? We'll be doing that. Second one is the deflection equation. Let me write the deflection equation in red. So we have this, you just need to plug in the value of C2 and that's it. That is the modified deflection equation or the original deflection equation. EIY is equal to RA x cube over 6 RA x cube over 6 minus MAX square over 2, yeah, draw line, plus 150 times of x minus 4 square over 2. So these are essentially two equations, right? The one in blue color is the slope equation and the one in red color is the deflection equations. Now we need to apply the boundary conditions again to get the value of RA and MA. The heat is really killing. I don't know whether you guys are able to realize this video making is an extremely difficult process. Looking at the camera, continuously speaking, it's really difficult. And especially when power does not help us, it's really difficult. Anyway, here we go. So that's the slope equation, that's the deflection equation. Now let us apply the another boundary condition, that is at x is equal to 6, that is at the far end, there at end B. Again, slope is going to be 0, dy over dx is going to be equal to 0. So when you plug in these values, this is left hand side, we'll have 0 is equal to 6 square is 36, 36 by 2 is 18. So this is going to be 18 times of RA, 6 times of MA minus 6 times of MA. And when you plug in the value of 6 over here, 6 minus 4 is 2 times of 150 is 300, so plus 300. Okay, so you can reframe this in a better fashion. You can write this as 18 times of RA minus 6 times of MA is equal to negative of 300. And let's say this is our equation number 1. We need to frame one more equation in RA and MA, so that we have two equations and two unknowns. Bravo. Okay, and let's do that. At x is equal to 6, again the deflection is going to be 0. When you do that, plug in the value 0 is equal to, is this visible or not, this portion? Let me see in the camera. Yes, it's visible, perfectly visible. So this is going to be 6 into 6 into 6, 6 and 6 will cancel out, 2 6's will remain. So this is going to be 36 RA. What about this? 6 square 36, 36 by 2 is 18 minus 18 MA minus 18 MA. What else? Okay, 6 minus 2. 6 minus 4 is 2. 2 into 2 by 2. So that's 2. 150 into 2 is 300. So plus 300 is equal to 0. So our second equation is something like this: 36 RA minus 18 MA. Again, this is equal to minus 300. Let me write this second equation: 36 RA minus 18 MA is equal to minus 300. Let's call this as our equation number 2. Now where are my notes? Let me check whether both the equations are correct or not. 18 RA minus 6 MA, 18 RA minus 6 MA barabar minus 300. Perfect. And then we've got 36 RA minus 18 MA is equal to minus 300. Perfect. We are going in the right direction. Okay, not to worry. 1 second. Please excuse me. Okay, now what to do? You just need to solve these two equations. When you solve these two equations, and let me just show that how this can be done. You just need to use this. What? Go to mode for equation, hit 5. First one. So the value of this is A1, B1, C1, A2, B2, C2. Just plug in the value of each and everything into this matrix. Okay, you can see this matrix. Plug in the value. So 18 here, minus 6 and minus 300, done. Then we have this 36 minus 18 minus 300. 36 minus 18 minus 300, and yeah. So the first value which we've got is minus 100 by 3. Minus 100 by 3. So approximately 33.33, isn't it? Minus 100 by 3. Where can I write this? Let's write it over here. Make some space. So the value of RA which we've got, RA is equal to, RA was first, isn't it? Yes, RA is equal to negative of minus 100 by 3. Well, that's a negative value which we've got. Strange. That means the direction which we chose, this upward direction that we chose, is wrong. We should have chosen the downward direction. So I'll change the sign, don't worry. Okay. Negative sign is just indicating that the direction that you chose is wrong. The original direction should be downwards, should have been downwards rather. Secondly, we've got this value of MA. Let me write. Let me check. So that's, what is this? This is X, that is RA. This is Y, that is MA. MA is working out as minus 50. Okay, again, the direction that you chose of MA was this. And based on this direction, we've got the value as minus 50. Minus 50 kilo Newton meter. That means the direction which we should have chosen is rather in a clockwise sense. That means both the directions which we had assumed were wrong. Now let me make this figure once again and let us start the business once again. So here we go. It's not going to be that tough. So we already have the equations. Let me have the entire beam. Yeah. Perfect. This is where we are going to have the couple. This is going to be your, what you call, okay, 150 kNm. Now we chose this direction. Answer came out with a negative sign. That means the direction should have been downward. So now we are choosing the downward direction. 100 over 3, obviously kilonewtons. Then this should have been in this direction. That's MA, that is 50 kNm. Pretty good. Now here we'll assume it to be in the upward direction, that is RB, and again here a hogging bending moment or a fixing moment, that is MB. There you go. Now what needs to be done is, now first of all let me just write this. This is end A, this is end C, and this is end B. Let me check ACB, ACB, yeah. Between A and C, this distance is 4 meters and this distance is 2 meters. That's fine. Now what? You just need to apply the equations of statics. Number one, you've got to apply this. Summation of all the forces in the direction of Y is equal to 0. So again, there are only two forces you need to work with. One is this RB and the other one is this 100 by 3. So if you watch, RB is upwards, take it as positive, 100 by 3 is downwards, take it as negative, minus 100 by 3 is equal to 0. From this equation, you can have the value of RA. RA obviously will work out as, not RA, have I written something wrong? FI, this is RB, not RA. RB. RA is known to us. Okay? RA is known to us, that is 100 by 3 in the downward direction. So RB will also be equal to 100 over 3 kilo Newton. So that's done. Now let's take the moment about a specific point. Which point? You can take any point. I'll be smart enough to use this point A, because when you take the moment about point A, this force does not come into the picture. Okay, since it is passing through point A itself, its moment is going to become 0. Now if you watch, we are going to start from let's say this RB. So RB multiplied by 6 anti-clockwise. So 6 times of RB. What is the value of RB? 100 over 3. 100 over 3. Done. What about this MB? It's clockwise, isn't it? Minus MB. Anything else? What about this moment at C? That is clockwise. Minus 150. What about this moment 50? This is clockwise. Minus 50. All of this is going to be equal to 0. You just need to solve this equation. It's pretty simple. And if you watch, 100 by 3, 3 twice, 3 2 is 6. Okay, so this is going to be 200. So this is plus 200 minus MB minus 150 minus 50 is minus 200. Oh, that's a beautiful result, and this means that the value of MB is obviously going to be equal to 0. It's a very important result, a very important conclusion. Okay, now you know MB is equal to 0. Apart from this, you also know RB is 100 by 3. 100 by 3. The direction that we chose was upward, and the answer is also positive. That means the upward direction is absolutely fine. You can also, what you can also do is, you can put this sign up. The second answer which we got from MA, this way. MA worked out as how much? Let me see. 50 kNm. 50 kNm. Okay, now forget about all those things. You have put it up over here. These directions are correct. These directions are also correct. You don't need to write all these answers. So the first 2 points are done. First 2 points said moment at fixed ends. That's done. And this reaction at fixed support, this is also done. Okay, that's the value of RB. You know the direction, that is correct. And that's the value of RA. Okay, that's MA and that's MB. Everything done. Second thing which we need to do is, or rather the third thing which we need to do is to draw the SF and BM diagram. How can this be approached? Again, fairly easy. Let me extend this. Okay, and let me extend this also. What else? Yeah. So let's kick off with the with the bending moment diagram only, right? Let me rub this. Okay. Where can I make some space? I need to make some space immediately. Okay. So watch this. Very interesting. And for finding the bending moment, again, you can follow the hogging and sagging approach, especially when you have forces. So if you have this force, if you're talking about this force, let's say we want to find the moment at C. If you talk about this force, so this will bend the beam in this direction. So it's a sagging bending moment. You have to take it as positive. No problem. But what about this bending moment? You won't be able to understand whether it is hogging or sagging. So in order to get rid of this confusion, what we'll try to do is we'll take this section. Either we can take this section from the right, get the value of shear forces and bending moment, or you can also take this section from the right also. Either from the left or from the right. If you take it from the left, bending moment anti-clockwise. If you take it from the right, bending moment clockwise. Okay. Now let's do the section from the right. Okay, let's do the section from the right and let's get the value of bending moment at B, at C. Then we'll take the section between A and C. Again calculate at C and at A. Let's follow this approach. For that I need to draw the diagram once again, and for that I need some space. Okay, let me draw it here. So this is the main diagram, guys. Okay, so we've got this RB. RB is how much? This is equal to 100 by 3. 100 by 3, and then we've got a couple acting over here. Magnitude is 150 kNm. Then we've got a force of fixing support over here. That is again 100 by 3. This is kilonewton, by the way. And then we've got this bending moment in this direction. This is the magnitude is 50 kNm. Just try to understand this. This is going to be point A, this is point C, and this rather is point B. What we'll try to do is we'll first take the section between these 2 points. We are taking the section from the right. If you are taking the section from the right, only this much portion of the beam has to be considered. Only this much portion. If you take the section from the right, this is going to be X. Okay, here this is going to be MX. Here obviously there is a force, the magnitude is 100 by 3. Okay, what you want to find is the bending moment at B and at C. So let's have the section between B and C. We'll have an equation in terms of X. You put the value of X is equal to 0, you'll find the bending moment at B. You put the value of X is equal to 2, you'll find the bending moment at C. This is the approach which we are going to follow. So just try to work this out. This is again very interesting. I'll show you how ultimately bending moments clearly worked out. And let me have some space. Let me have some more space because I'll need it. किधर गया रुमाल? Okay, so you can also work out the shear force, guys, not to worry. The shear force will be in this direction. Okay, if you take this section from the side, right and left hand side, the shear force is downwards and the bending moment is anti-clockwise. So this can essentially be written as Vx. Okay, so what we've considered right now is that we've taken the section. Let me write it over here. Section between B and C, rather let's say C and B. When you do that, the first thing we need to do is summation of moments is equal to 0. So let's take the moment about this point. Okay, about this point. Okay, this is the section. If you watch, automatically this is acting mx clockwise minus mx. Fine. Then we've got this 100 by 3 anti-clockwise. Okay, 100 by 3 multiplied by x. So this is going to be plus 100x over 3 equals to 0. That's it. That's it. So you've got the moment equation, and what you can do is you can write this again as mx is equal to 100x over 3. Now when you put the value of x is equal to 0, so you compress this. You compress this, x is going to become 0, and x is equal to 0, we've got the point B. So automatically you'll have the moment at B, which is going to work out as 0. You put x is equal to 0 over here, moment at B is 0, and we already know that. Okay, so this has been verified. Secondly, when you put the value of x is equal to 2, x is equal to 2, increase this, stretch it, and we've got the value of x is equal to 2, that is at point C. When you put this, you're going to get the value as, where is it, 100 into 2 is obviously 200. So this is going to be 200 over 3. Done. Let's do this again. Now what we'll do is we'll take this section over here. I don't know if this much portion is going to be visible. Let me check. Yes, some portion. I need to be very clever. Okay, so this much portion of the beam is visible now. So we have taken the section from the right, that's x. Okay, somewhere here you have the clockwise couple. This is 150 K N M. Then you've got this reaction over here. This is nothing but 100 by 3, and then you've got a couple, and this is how much? Maybe I'm forgetting something. Couple is obviously 0. Even here the magnitude was 0. So it doesn't matter if you apply it or not. Let us not apply it. Okay, forget about it. It's 0, absolutely. Don't worry about that. Anyway, so let's take the section about this point. Okay, let's take the moment. Section between, now we shall have the section between A and C. Let's take the moment is equal to 0. When you do that, what you will have is clockwise. This is clockwise, okay? So minus mx 100 by 3 multiplied by x anti-clockwise. So plus 100x over 3. What else? 150 kilonewton meter. So this is in the clockwise nature. So minus 150. All of this is going to be equal to 0. You just need to frame this in a better fashion. We can rewrite this as mx is equal to 100x over 3 minus 150. Now, so here is the slider. You compress it. At x is equal to what? X is equal to 2, you will get moment at C, and x is equal to A, you will get moment at A. So just write this, x is equal to 2, you will get the moment at C. We shall find it out. And at x is equal to 6, we will have the moment at A, which we already know, by the way. Okay, so let's just plug in x is equal to 2, 200 over 3. Okay, so this is going to be 200 over 3, 2 into 100, 200 over 3 minus 150. So this is working out as minus 250 by 3, that is minus 83.33. Okay, minus 250, where is it? Minus 250 by 3. What about this? If you plug in the value of x is equal to 6, 6 divide by 3 is 2. 2 into 100 is 200. 200 minus 150 is 50. Obviously, you're going to get that value again, 50. Okay, same value. Don't worry. 50 in a positive sense. You have now everything to draw the final bending moment diagram, and let me show that how it can be essentially done. So let me finally draw the bending moment diagram. Okay, this is BMD, final bending moment diagram, straight away. Now you know very well, at this point the bending moment is 0. At point B the bending moment is 0. Even here I didn't put up any bending moment, as it is 0, so makes no difference. Okay, MB 0. What about MA? MA which we have achieved, MA that we've achieved is 50. Okay, so right here 50. So let's take this point. This is 50. So everything has been written in kilonewton meter. That's it. Moment at C, that is minus 250 by 3. So first of all we got this value. Let me go step by step. 0, 2, 2, 6. 0, 0. 2, 200 by 3. 200 by 3, by the way, is, let me do this, 200 divided by 3, this is working out as 66.66. So slightly above. Here, this is 200 by 3. Then after this we got this value. Okay, since there is a couple acting, you are going to have two different bending moments. This is minus 250 by 3. So minus 250 by 3. How much is 250 by 3, by the way? This is 83.33. So slightly more. Somewhere here. Here. 250 by 3. Yeah. So basically this is where you need to go. Here 0, 0, then 200 by 3, then minus 250 by 3, and then 50. 0, then this, then you need to drop. You need to reach here, and then you need to go over this place. Okay, manageable. Right, so this is the entire calculation which needs to be worked out, and what you can do now, you can just shade it to make it look more beautiful. Okay, this is obviously positive, negative, and positive. So I now leave the shear force diagram to you guys. It's very easy. I don't have any space, otherwise I would have certainly drawn it. What you can do is you can start from anywhere. So it's going to be something like this. If I can just make it, where can I do this? Better to note all of these things down. Okay, shear force diagram would be something like this. Depends on what sign convention that you follow. Here, positive. It could be in the downward direction also, in the negative sense also. The values are going to be 100 by 3, and here also 100 by 3. So this is how the shear force diagram is going to be made. Okay, if you start from this point, which point? If you start from here, let's say from the right hand side, start from here, RB. So you need to go upwards, how much? 100 by 3, and then there is absolutely no force between B and A. Then you need to go straight, isn't it? And then you need to come down, how much? 100 by 3. So you are going to end up here only. So this is the 0th level. Okay, so if you start making it from this right hand side, you are going to end up with this shear force diagram, and that's it. That's it. So guys, that was all for today. I'll see you in the next video. Until then, take care, have a nice day, keep learning, keep watching, and thank you.